Yeah, so today I'm here to talk about some of the work we do, which is sort of centered on evolved stars. So the centerpieces are sort of low mass dying stars, but it's kind of a amalgamation of different research projects that actually led us to sort of coming across the idea that could you actually have planet formation in an entirely different astrophysical site as opposed to the traditional young stars, that is what is expected. So before I go ahead, I'd like to just introduce my student team, a fantastic group of students. As you can see, my research group, we work on three varied type of topics. There's the chemistry and the origin of elements sort of topic, and then there's something which I'll talk to you about today, which is really about understanding disk structures around evolved binaries. And then we also have some work being done on chromospheric activity in stars. So anything to do with stars, spectroscopy, any sort of observational techniques, we love that, and that's kind of what we do. So I also have collaborators who've contributed to a lot of the work that I'm talking about today, but you know, we'll see how that all goes. So I thought I'd jot down my key questions because I don't come to Monash often and talk about my research. So a lot of the key questions, as you see, the first three especially, are centered around the late stages of evolution and sort of understanding how a lot of the elements in the universe are created, how do these elements sort of condense onto dust, and how is that dust injected to the ISM, and then from that you've got new stars being formed. So more recently we've been working quite a bit on understanding the metamorphosis from the AGB phase to the PIONIER phase. Often this is in fact one of the most critical phases, the AGB phase, because it is responsible for producing in low mass stars the majority of the chemical elements you see in the periodic table. But there's always been groups working on it quite distinctly. So what we've been trying to do is we've been trying to understand element production during the AGB phase, including dust. How does that element and then dust evolve? And eventually, how is that then contributing to the dust budget in the cosmos? Today I'm going to be talking about something that's a little bit different. Now for the first three questions we focus a lot on single stars because these are the stars that are kind of contributing to making a lot of the elements. When you put a companion in the mix, there's a lot of complications, including pollution of the elements that are made. So it's a bit hard to understand how binarity affects chemistry. We do that. But I thought in today's lecture I'll talk more about understanding the structure of these binary systems in evolved stars, and more very interestingly, something that's relatively new that's propped up is really understanding these so-called second generation protoplanetary disks around dying binary stars. Now dying binary stars is of course a very, very large class of objects. It could be anything from AGB, post-AGB stars or barium stars, SAM stars, but we're mainly focusing on anything that's evolved off the giant branch like the AGB or the RGB phase, but I'll get to that. Now here's my setting the scene. Interestingly, exoplanets were first discovered around pulsar hosts. So if you think about where you might find exoplanets, we traditionally think of young stars hosting them, but the very first discoveries way back in the 1990s was discovering planets around pulsars. Now, what is critical in this particular case is the fact that pulsars have accretion disks, and essentially the key ingredient for planet formation is really a disk, which is hence the name protoplanetary disk of some sort. Again, this is something, it's like preaching to the converted. I don't have to talk about this as much, but a lot of exoplanets, including, say, our solar system, is orbiting around young stars. So here's an image of a T-Tauri with ALMA, the undisputable machine to sort of study exoplanets and disk structures. So what you see here is one of the two planets around this T-Tauri system. And in the HR diagram here, I show the surface temperature and luminosity. And typically when you study exoplanets around young stars, you're looking at young stars that are either on the main sequence or a little beyond the main sequence, though there are exceptions where exoplanets have also been found around a few white dwarf systems like NN-SUR. So the critical takeaway message is, of course, beautiful disks. Now here's some flashy ALMA pictures again. So you've got an ALMA continuum image of HL tau. You've got an image of TW Hydrae with gaps and a few cavities. And then you've got the continuum submillimeter emission that I showed before. So it goes to kind of show that planet forming sites are essentially, or the cradles of planet formation are essentially these disks. Now, where exactly can you see these disks? Where else do you see these disks? That's the question probably we want to ask ourselves if we're really interested in hunting for alternative planet formation sites. And another question to ask ourselves is there some sort of a pattern or similarity between young star PPDs, the protoplanetary disks, and disks that you find around evolved stars, for example? So hopefully at the end of the next 40 minutes or so, I'm able to kind of showcase similarities between young star disks and evolved star disks, leading us to the conclusion that we might be sitting on a second chance for planet formation in low mass dying stars. Now, I like this sort of montage from Benstein et al. Because it kind of showcases the diversity in protoplanetary disks around YSOs. So there is not one sort of image, there's multiple. And I think this kind of puts to light that disks can be varied, and understanding the morphology and picking out characteristics that support planet formation is what we're looking for. So traditionally, star-forming disks, how do you find them? I don't have to spend much time. You've got star formation, you've got accretion onto forming the giant molecular cloud, forming the star, and you've got this disk which is sort of also seen in something like our solar system. Now I'm going to start introducing the objects that I'm interested in, the protagonists of this seminar today, which is looking something like this, right? So you've got an evolved binary system where a star is an AGB, and you've got like a main sequence companion, and some magical binary interaction takes place. As Dan and I and Christoph were talking about earlier, it's very, very hard to kind of hypothesize or form a theoretical framework for how you could make and sustain this sort of a disk. But imagining you do, because the observations say that, you know, we observe it, we're finding some sort of a Roche lobe overflow with stable mass transfer, because the disk is still stable, resulting in the formation of a circumbinary disk. So when you think of these systems, you're thinking of the binary system in the center with a circumbinary disk around it. So where exactly are these in context to the HR diagram? So once again, as I said, it's typically in the AGB, and you also expect this in the RGB. More recently, we've got observations for this, but just sticking to the AGB phase, when your star is beginning to fill up its Roche lobe, that's essentially where binary interaction can terminate the AGB lifetime, resulting in something like what I've depicted in my little cartoon. So, as I said, what are the interaction mechanisms? Now, there's a couple, and I got this slide from Ono. I forgot to credit him for that. But there's multiple binary interaction channels, but the goal or the tricky challenge has been really being able to sustain a disk that you create. So that's sort of an open question, and that's not something I'll be answering in today's seminar, because that is sort of work in progress, but we haven't had much closure when it comes to understanding the theoretical framework of the disk. But what I can convince you with is more so observations. So what we have is observations that are near-infrared interferometric observations, as well as high angular resolution direct imaging with extreme AO to be able to sort of resolve and also constrain what these disks look like. Now, something to keep in mind is, and I'll go into it a little bit in detail later, when we do model these disks, for example, the interferometric data, we use passively irradiated models that are used for YSO disks, and we use that in our radiative transfer modeling, and that actually gives us quite a good fit to reproduce the observations. So what you're seeing here is like H-band reconstruction, which is essentially the near infrared. So you're looking at the inner parts of the disk. So you're sort of reproducing the dust that sits in the inner part of the disk of these post-AGB binaries. Here, on the other hand, because of the spatial resolution of sphere, which is around a couple of, say, anywhere below 100 milliarc seconds, you're seeing all the way to the extended structure. So I have an image later that puts these two together, where you see we're sort of building the disk from the inner parts to the outer parts. But the observations have allowed us to come up with a little bit of a understanding of what this disk might look like, also taking motivation from what the protoplanetary disk structure looks like. So this is what we're essentially looking at. So it's quite a complex system. You've got the post-AGB star, you've got a companion. Now I'll talk a little bit about how we constrain the nature and orbital parameters of this system, but this is just like a showcase to get everybody the overview picture. And what we see is depleted gas, and this is not, we resolve this through spectroscopy, so we don't quite have too many ALMA observations in imaging for this, but through spectroscopy we can detect the depleted gas. And so far, based on near-infrared interferometric observations, we find that the dust inner rim sits around 1 to 15 AU and extends all the way up to about 100 AU. Now, interestingly, what we also observe is, because you've got accretion from the primary to the companion, you have a circumcompanion disk from which we have jets, essentially medium velocity outflows of a few 100 kilometers per second. So if you put this in context, here's an image of HARO 65b, a protoplanetary disk around the YSO, and here's a post-AGB star, which is AR-PUP, both essentially from sphere, and you can see that you can really seek analogies or parallels between the shape of these two disks. Now both of them are quite edge-on, so what you're really seeing here is like the mid-plane of the disk. We've had people work, including the group at Macquarie and here, work on simulations of these disks. As I said before, the results have so far been, you're sort of getting to the point where you make the disk, but keeping the disk stable and long-lived is a bit of a challenge. But we'll leave that out for now and see what comes out of that in the next couple of months. So before I move on, I just wanted to put this in context, because I am making a comparison between disks around post-AGB binary stars and young stellar objects. So I thought something like this kind of brings it all together to give us an idea of the similarities and also the differences between these two systems. So for a lot of the parameters, they're actually quite similar. Now where they differ is when it comes to disk mass. The disks around post-AGB and you'll see post-RGB binaries are much less, are a little less massive in relative to, again, this is a bit of a spread, so they do overlap a little bit. And the lifetimes, again, are different. So PPDs have longer lifetimes than post-AGB binary disks. Here's something to put things in scale. So as I said, we also use the same passively irradiated model from Doulemont. So in terms of how the disk structure aligns, they're sort of similar, but again, the scales are a little bit different. Because our stars are much more luminous, so the primary for us is a giant, so you expect the disk to start at further distances. So you see our disks, if they're a full disk without any cavity, and I'll get to that in just a bit, it starts off essentially at around sublimation radii, as a bit different to what you see for the protoplanetary disks. So this is kind of my introduction to what I'm going to talk about, and hopefully bringing us into speed as to why we make these analogies. And I think the strategy is, if it looks like a duck and it quacks like a duck, it's probably a duck. So I think that's the whole strategy, and that's sort of something you have to do when you're trying to come up with like a new science possibility where you don't have direct observations for the exoplanet or something that's, you know, in the circumbinary disk. I wanted to take a minute to talk about the sample size, because this is often a question that pops up. Now, post-AGB studies started way back in the 1980s, but they've been very piecemeal and scattered. More towards the 2010-ish, we started doing more survey studies, and that took off more so. Something I did also for my PhD, the second part of it was really hunt for post-AGB stars quite systematically in our galaxy, LMC and SMC. It took more than half a PhD to do that, so it's quite a painstaking endeavor, but now with neural networks and stuff, there's a more efficient way to do it, so we might go down that path again. But what we did back at that time was essentially looking for photometric characteristics that bring anything that could be a post-AGB candidate together as your initial selection. And what we find is that M stars, C stars, PNE quasars, and also post-AGB stars, and more importantly YSOs, all of them sit in the same part of the HR diagram. So then it had to come down to weeding out disentangling the other objects from our systems, and we had to do that with spectroscopy, because spectra will immediately reveal characteristics that are unique to different classes of objects. We capitalized very heavily on the AAT, the AA omega spectrographs, because it's multi-fiber, so you can get a lot of data looking at 2-degree fields in the sky. So it's not by in any means a complete survey. At the moment, survey completeness sits at about 50% for the LMC, SMC, and the galaxy is more like 25%. So the southern part of the galaxy. So we still landed up with quite a lot of targets. So we've got a few hundred candidates in each of the galaxies. Now, something to keep in mind is you're not going to find millions of these objects, because if you look at the lifetimes of these objects, for every 1,000 AGB stars, you're going to find one post-AGB star, because the lifetime of the post-AGB phase is about 10,000 years. So that's quite short in cosmic lifetimes. And if you add binarity in the mix, you could prolong the lifetime because of the accretion or the reaccretion, but not by a lot. So in general, you're not going to find a lot, but what we've achieved with the small target list or modest target list has been quite a lot. Now here I want to take a detour, because I've been using the word post-RGB stars, and this is how that came about. So until 2016, we did not have observations, or we did not believe that you could have RGB stars that terminate their RGB lifetime. Models, population synthesis binary models, predicted that you could have binarity terminating the RGB, but we hadn't observed them. But with the survey, and because the LMC SMC has quite distinct luminosities, we were able to get samples of post-RGB stars. So this came to show us that in an HR diagram, basic astronomy 101, when you've got binary interaction, in some cases, depending on the binary parameters, you can have binary filling up the Roche lobe and terminating evolution on the RGB. So it goes off the RGB, it doesn't yet go up to the AGB. What does that mean for the star? We still find that these systems have disks, very similar to the post-AGB disks, but of course the masses and the chemistry is a little bit different. So I'll just keep rolling with this. So how did we confirm that they're binaries? So I'm at a point of my talk where I've said, so there's the goal of trying to establish that, you know, these evolved stars have circumbinary disks that are similar to protoplanetary disks. I've sort of presented the sample we have. The next important question is, well, how do we know they're binaries to start off with? Now, this was possible entirely because of the PI, Hans van Winkel from KU Leuven. They had their own little telescope, so it does pay to have your own telescope. It's a tiny telescope, but it's very efficient. They've been doing radio velocity monitoring of these systems since 2009, but we've only had results 10 years later because these binaries are long period orbits, so anywhere between 500 and 1,500 days. So we needed to monitor them for a long period to be able to establish accurate orbital parameters. So what you see here is radio velocity on the y-axis and phase, and these are residuals. The residuals are important for us because if you look at where the post-AGBs and post-RGBs lie on an HR diagram, this is your population 2 instability strip, and they do sort of transit around the population 2 Cepheids. So they do show type 2 Cepheid type of pulsations like RV Tauri type and so on. So we were quite confident with the binarity aspect of it. We had orbits, and it came down to understanding these orbital parameters. And this is where it started getting quite complicated. So what I'm showing you here is work from Ni et al. It's population synthesis it's a population synthesis orbital period distribution for a bunch of evolutionary class of objects. So you've got PNE in black, close binary PNE in blue, post-RGB predicted, and early AGB, orbital period distributions in gray and cyan, and double degenerates in red. So the theoretical framework was that you have common envelope, and this can sort of result in spiral or wind transfer. So this is what you have from population synthesis modeling predictions. Now what we found was this. So this is where our observational orbital periods for the post-AGB and post-RGB binaries actually sat. So in a sense, we landed up determining orbits with periods that were least predicted for post-AGB and post-RGB binaries. This did go to tell us, and Dan confirmed this during my talk with him yesterday, that you do need new binary interaction physics, because otherwise it's really very hard to understand how you actually make these systems. Some other interesting results from the orbital parameter study, and this was done by a PhD student in KU Leuven, where I was doing a postdoctoral fellowship there. So this is an eccentricity period plot, period in days, and this kind of tells you that there's kind of like these binaries have rather eccentric orbits. You do have ones that are sort of circularized, but mainly they're also quite highly eccentric. So it's a range of eccentricities. Now there is sort of like a pattern there, like a bimodal distribution, but we don't read much into it because, as I said, this is not the full sample of post-AGB binaries. It could very well be an observational bias because of what you can observe with respect to the inclination and the eccentricity. Now here's the Gaussian distribution of what the secondary companion could be. The peak of the Gaussian is around 1 solar mass, so ideally we go ahead with the understanding that their companions are a main sequence, so they don't quite interfere when you study spectroscopy or imaging of the main star, which is the post-AGB star. However, something to keep in mind is that the distribution does range anywhere from around 0.1 up to about 2.8 or so. And that also has a significant amount of stars, but we just assume that it's a main sequence companion. Now, sort of pressing along in the same sort of understanding the disks, so I'm kind of giving a bit of an overview of these disk structures really. So I showed you this as a bit of a cartoon before, but if you translate that into a spectral energy distribution, flux on the y-axis and wavelength, you really see the star peaking at optical sort of wavelengths, and you see a near-infrared excess, which is normally, even for the YSOs, indicative of hot dust in a disk. Now, these disks have been studied through various sort of observational techniques. Now the disks are quite fat and puffed up. They have large infrared excesses, as I said, and also with near infrared and sort of Spitzer spectroscopy, we were able to get the size of grains, not entirely yet, but we sort of could get an estimate that they were large crystalline kind of grain sizes. ALMA observations from a group in Spain, Valentin Bujarabal et al., did confirm that they use CO velocity maps, and they were able to confirm that the disks are quite stable and in Keplerian rotation. So very similar to protoplanetary disks. Now, more recently, we had a postdoc start in Leuven who came to us from the protoplanetary community, and this is Jacques Kluska, for those of you who know him. With the expertise of protoplanetary disks, he was able to kind of expand what we knew about these disks into a more robust comparison to protoplanetary disks. So in a study we put out in 2022, what we found was that the post-AGB and post-RGB binary disks have different subsets. So you've got those where the inner rim of the disk is sitting at sublimation radii or radius, and you've got those where the inner rim of the disk is sitting somewhere between 3 to 7 times sublimation radius. So you've got this massive cavity or a gap or whatever you'd like to call it. So pictorially, that's kind of what we think they look like. Now, one thing to keep in mind is that these stars, as I said, they have a range in luminosities, as I showed you in the HR diagram. So that also, of course, determines where the inner rim of the disk actually starts. But using photometric colors and also SED types, we were able to classify the post-AGB binary disks into 2 main subsets. We call them the full disks and the transition disks. Now, the transition disks, because just like you observe in the protoplanetary disks, they have quite a large cavity or a gap, again, indicative normally in that for YSOs of possible planet formation. So just to give you a bit of an idea, this is kind of what they look like. You've got the full disk, you've got the transition disks, and you've got something that's more like debris disks, but these are not gas poor, they're more dust poor. So initially, when this paper came out, we were thinking that, in a way, these disks evolve eventually into this. Maybe there's some sort of an evolution going on there. But as we study these objects and look at their different chemistries and structures, we begin to think that maybe they're quite independent channels of formation and possibly evolve into something like this. But that's, again, it's sort of debatable. So this is bad animation. So here you go. So I thought we've looked at the SEDs, and I thought what I'd like to establish next is a little bit of the chemistry, because again, what we're trying to do is really seek parallels between the evolved stars and the young stars. Now, this is looking at the main star's surface. We do this with high-resolution optical and near-infrared spectroscopy. Now, if you are working on AGB stars, you know that AGB stars produce carbon, oxygen, in some cases nitrogen if hot bottom burning is working, and you've got S process, again, depending upon the parameters and metallicity. What we find for these binaries in varying efficiencies is a pattern that we call chemical depletion, where you have a depletion of refractory elements, and the volatiles are more abundant. So these just have different condensation temperatures. And this is kind of a trend that we see. You'll see from the next few slides that this is very, very similar to what we see in YSOs. But essentially what you're seeing here for the post-AGB stars is it kind of mimics the gas phase abundance of the ISM. That's essentially the pattern that we see. And depletion can be very efficient, wherein they result in systems with Fe/H of -5. So these are not intrinsically metal poor, they're extrinsically metal poor because of the binary interaction. There's not a lot of studies of their infrared spectra. There is a few, and the spectra often show that it's very dominated by silicon carbide grains. So you can see the 10 micron silicate feature very prominent. So it's a very crystalline kind of chemistry that we're able to observe. I just wanted to quickly show this to again remind you that it's not one star, it's a sample. And what makes it interesting is it's quite a diversity of depletion efficiencies. So what I'm plotting here is zinc, which is a volatile element, and titanium, which is a relatively heavier element and a refractory. So the ratio tells me how efficient depletion is. So you can see there's a whole range of depletion, and it has little to do with temperature, because effective temperature of the star, because there's quite a spread in the sample. We've also looked at depletion efficiencies between full disks and transition disks, and also post-RGB and post-AGB. It's quite a mix, and there's no real correlations. So Max, who's one of my students, is putting out a paper soon that has a really good cross-correlation analysis. So at some point, I hope he's able to show you the results for that. So I just thought I'd draw parallels once again, because that's kind of been the theme of my talk. So I just wanted to show you that this is what I showed you 2 slides ago with the chemical depletion pattern in post-AGB binaries. And comparing these to young stars and the ISM, as I said, it's really kind of mimicking the gas phase abundance in the ISM. So we're not very surprised there. But if you look at the young stars, there's the full disks and the transition disks, and this chemical depletion pattern is quite similar to what you see around transition disks young stars. So the difference is about greater than 1 dec between the two, the CNO and in this case the heavier elements, and we see something very similar as well. Now how does this happen? Again, we don't have an answer to that, so we have a student working on understanding the theoretical interpretation of depletion. In YSOs, what is thought to happen is some sort of gas and dust separation in the disk. So what is thought to happen is you have some sort of a gap caused by a planet, and then you've got the dust that is trapped away, and then you've got gas that is then reaccreted onto the surface of a star. For us, we think there's the circumbinary disk, and something must be happening in the disk where you're somehow fractionating the gas and dust. The dust condenses onto grains, gets blown away. The gas, the clean gas, gets reaccreted back, which is why you see that depletion sort of pattern. Now this would make sense if it was really the case, because then all your transition disks would show depletion. But what we find is, irrespective of whether you're looking at, I'll go back to this plot, irrespective of whether you're looking at transition or full disks, we see depletion across the board. These do tend to be more depleted, but that's not to say that the full disks are not depleted. So again, that just adds a little bit of complexity in there. Okay, so far we've covered sort of, you know, the systems, the spectral energy distribution shapes that confirm a presence of a circumbinary disk. I've tried to draw analogies in terms of surface chemistry of the star and a little bit of the dust and gas chemistry. In order to be able to study the disk structure more, what was obviously important was being able to explore the disk morphology, grain sizes using interferometric observations and also high angular resolution imaging observations. Now, I'm not an interferometrist, but I do work closely, and over the years I've been involved in a lot of the work that is being done simply to understand these disks. And again, it goes down to saying how learning new techniques can just totally broaden the way your science questions take directions. So together with the group in Leuven, we've been collecting interferometric data from H to N band. We've been using MIDI, and PIONIER, gravity and MATISSE. So I've been doing spectroscopy for probably 7 years of my career, and I never went to Paranal. But the minute I started working on interferometry, I went to Parnell like 3 times to get data. So I then told a lot of my students, if you really want to go to Parnell, and then this is what you have to be working on. I don't know if that still holds, but this was the case, at least for me. And I absolutely enjoyed it. Okay, so coming to understanding, you know, these disks using interferometric data sets, what have we learned? So you're obviously looking at 1 milliarcsecond resolution around about, and you're benefiting from the small ATs, or, well, we've never really used the UTs for this, but mainly the ATs. You're benefiting from combining light from all 4 telescopes. I'm not going to show a lot of the results. I decided to kind of curate the ones that are most relevant and ones I've shown before, so it's not too intense. But basically what you're doing with the near-infrared interferometric imaging is, as I said before, so that's your resolution element there. So you're looking at anything that's less than about 10 milliarcseconds. So anything that's between a few AU to about 10 AU is what you're looking at. Just to put this in context, these systems, we don't have distances to a lot of them. So we assume them to be around 1 kiloparsec to 4 kiloparsec. That's kind of what we assume. Gaia doesn't give us accurate distances just as yet, because these are kind of orbiting, and their orbits are around 1,500 days-ish. So the parallax interferes with the orbit, so you can't really get accurate parallaxes for them. So the distances, we'll have to wait maybe for Gaia DR4. For the small orbit systems, we do have distances, and we've been able to work better with those systems. So as I said, what I'm showing you here is really the, we've really been able to kind of resolve the inner rim of the circumbinary disk. Now there's a small flux, that contribution that you see from here. I'd like to note that we don't resolve the stars. They're just put here for understanding purposes. We've just artificially placed the stars with the separation of about anywhere between 0.3 to about 2 AU. But we've just placed them there. We don't really resolve them at all. Anyway, so what we do see is this extra flux, and we think that this could really be coming from the circumcompanion that's kind of launching the jets. So what we've done more recently over the last 2 years, and probably very interesting for me as well as a learning and also as an understanding of how this research is taking shape, is we were successful in getting a large program with PIONIER and gravity, and the main goal for this was really resolving the inner rims of these disks and understanding whether is there really a circumcompanion accretion, what's going on there. So a lot of this work was led by Jacques, of course, and with contribution from the whole collaboration for different aspects of how we've been reducing the data. So the many exciting reasons for me to be at Monash is also Christoph. So I've been hoping that we can sort of look at MacForce for the radiative transfer modeling. We now do it with a more sort of a homegrown approach, which is probably, yeah, there's more effective ways of doing that. Okay, so just as what we really did, so as I said before, we used RT models for protoplanetary disks to be able to model our systems, and we were really able to reproduce the flux contributions from the inner rim, the sizes of the inner rim, and not so much the over-resolved emissions, but, you know, for the majority of the part, we were able to find that RT models from protoplanetary disks adapted quite well for us. Now, something that we did find from a study like this is, again, so this is essentially, maybe I should take a moment here. So there's near-infrared data in various bands. Now, I'm showing you obviously the best target we have. We don't have this data set for the entire sample, but we do have it for more than 10 stars, which is actually quite a gold mine if you think about the entire sample in itself. So what we're really finding from this study here is that the inner rim radii are really very different for the full and transition disks, as I said before. So that's one of the interesting results for this. And we've also been able to constrain things like disk sizes and so on. I just wanted to quickly show this plot. We have just recently begun to understand that there is a time evolution of the disk morphology. So this is taken over a period of time, over say a couple of months, and we do find that there is really a change in the shape and the emission from the circumbinary disks. So we're sort of in the process of interpreting this, and the way forward for interferometry is definitely ALMA, but we're sort of, yeah, there's a group in Spain doing that, but we haven't yet quite gotten our hands on it, and probably something we should talk about. Okay, so in the last few minutes that I have, I thought I'd just like to also highlight some of the other work we've been doing in establishing the disk structure. So the near interferometry gives us really the inner rim. Using, for example, high angular resolution imaging with sphere, you're looking at structures that are much more extended, so anything greater than about 30 AU. So you're looking at the outer extended parts of these disks. The benefit is essentially you've got the main star, you've got a circumbinary disk around it. So what you're hoping is going to happen, and what happens essentially with imaging, is you've got light bouncing off your main star into the dust particles in the disk, and then you've got that scattered light is what you're observing. If you put polarimetry in the mix, you're able to block off the stellar light and just observe only starlight. So what you're looking at is essentially something just like that. So you've got the orientation of polarization along the disk, and we're able to sort of study the outer parts of the disk. Now this is work done by Katja, a student from Macquarie. Some of you might have heard her talk at ACES, but she will also be coming back to Monash, so I won't go into many details of the talk, but I would like to say though that again we've got similar target samples, and these stars are the same targets for which we have near infrared interferometry, with the goal of building the disk structure from near IR to extended. So having ALMA on the even more larger disk structure would essentially be the next thing the obvious next thing to do. So I'm just thinking if there's anything else I wanted to say. I think I'll just show maybe a plot or two and then summarize. So this is results from Katja's work analyzing IRDIS data. The overarching goals or the takeaway messages is basically we've got complex morphologies around these post-AGB binaries. So you can see anything with arcs and multiple wing structures. We also find that the transition disks in the sample are a little bit more asymmetrical and more complex than the more full disk systems. They kind of agree quite well with the sphere imaging data results for YSOs, which has also been quite interesting for us. And we also find that there is a bit of a metallicity trend. So the transition disks that tend to be more metal poor tend to have lower dust than the more metal rich systems, which essentially indicates that gas and dust formation does depend a bit on metallicity. I'd skip to this plot here, which is, so what we've done here is we've plotted your Q factor, the linear polarized brightness with protoplanetary disks around YSOs. So we've got PPDs and we've got our objects. So our object's the one on top. So what we do find is they're within the ballpark of PPDs, and post-AGB systems, at least this one, shows relatively higher, well, they're sort of sitting along the same region as the brightest PPDs. In terms of dust aggregates, again, they're quite similar. So there's, we do find a lot of forward scattering in these systems, which is indicative of larger grain sizes. And we've made a bit of an estimate, so we're looking at micron sizes and in some cases sub-micron sizes. So to put it all together, I'd just like to end with showing this summary of what we've got observationally. So you can see we've been trying to establish the parameters and characteristics of the primary star, mainly with spectroscopy. We've been then studying the disk through different techniques. I do have ALMA here, and that's because it's kind of work in progress, but I didn't talk much about it, maybe for another time. But this is sort of the system or the set of observations we have, and we're quite well positioned to be able to really get the last few missing pieces and do some modeling on these systems to be able to get a theoretical interpretation. So the goal is really this, and a lot of what the people at Monash do resonates with our goals. So I think there's a lot to gain from this work and the collaboration here. So we want to measure the morphology of these observed second generation planet forming disks. The idea is to build a theoretical model for second generation planet formation and build nexus between planet formation in young and evolved stars. The beauty, or in my opinion at least, is the fact that you are in a realm where you're sort of having new innovative astrophysical sites to test existing planet formation theories. And I think maybe we're just seeing the tip of the iceberg here, and there's a lot more of these candidates, and there's other evolved stars with disks that have similar potential. I'll just stop here. Thank you for your attention.
When you showed the separation of the stars,
yeah,
they're quite close together. Like that's closer than the size of an AGB star during the AGB phase. So is it likely they're first common envelope or mystery?
Well, so A sin I is around, like I said, 0.3 to 1 or 2 AU. There's a difference. Yeah, I mean, I think the issue with post-common envelope would then be, you know, how do you not circularize your orbits, because the eccentricities of these systems are, you know, anywhere between 0.2 and 0.4, 0.5. So typically you'd find spiral in a lot of the times, but we don't see that. And the other thing is the orbits, yeah, the separations are small, but they're quite large orbital periods. So again, but mainly I'd say the eccentricity is something that you're, you know, sort of thinking about in that case. And we don't see a lot of spiral in going on. So central stars of PIONIER are often, you know, spiral in systems, but again, we don't see that for these systems. So, yeah. I just want to say there's a system called UMON. I don't know if it rings a bell, but in that particular system, they have detected X-ray emission, and that can obviously only come from a companion because the main star is obviously, you know, a giant. So that could be one of those stars in the second part of the Gaussian distribution with a more stronger companion, and that has a very it has a very typical eccentricity orbit. So, yeah.
What do these things turn into? So, like, if you were to observe them later in their life, what sort of thing does this end up as?
Yeah, so I guess these would, I mean, there's different phases in which you can take these systems. So a system like the red rectangle, for example. So I guess it would turn into something that is like a PNE, but the central star would likely just be a bit different, possibly. Or maybe there is eventually some sort of orbital, you know, parameter shrinkage or something. But yeah, we've got a lot of systems where, and I kind of showed them, they're similar SEDs, but they're quite dust poor. So we do think that there's the dust has to dissipate eventually. And we've got systems like the water fountain, and they have, based on their stellar parameters, they're known to be post-AGB. successors. So I'm guessing some sort of planetary nebula sort of thing is what I'm guessing. But they could also eventually, you know, be white dwarf systems. It would just depend on whether it's a CO white dwarf or a helium white dwarf, depending on whether it's a post-AGB. I mean, if you look at the PNE sample, it's really diverse. So there's a lot of diversity in PNE morphologies. So it's possible that this is something that goes in there. But somehow you have a shrinking of orbits.
So very naively though, is there any evidence for planets around double white dwarfs? Or?
Well, yes, there is. So NN-SUR is one of those systems which is a double white dwarf. And I think the thing with double white dwarfs is, and at some point this was a possible science case that Hans and I were talking about for ELISA, which is using them as gravitational wave, detection for the mergers. But there's not a lot of them, so white dwarf binaries are quite rare. But having even one NN-SUR, which is very well known and well studied, is an indication that that exists. So it's a possible evolutionary channel. But they're quite hard to detect in the optical. You need, because you first need to characterize them spectroscopically, and you're always constrained by by the observing.
Thanks for the talk. From an AGB variability perspective, I guess there's, I was interested in the orbital periods that were kind of found for the first.
Yeah.
Was it post-AGB and AGB?
Yeah, they're sort of at this stage, so probably I should say a lot of the radial velocity studies and the interferometric studies have only been done for, and the sphere work is all galactic objects. So for the LMC, we just don't have the capacity to do this kind because we don't have a telescope like this. But yeah, so this one I'm guessing, yeah.
Yeah, I guess if you're aware, there's the long secondary period.
Yeah.
In, I guess you see in the period luminosity diagrams for AGB stars. They're kind of in the same orbital period range. Would you see any connection there?
So often the long secondary periods are coming from nonlinear pulsations and mass loss that happens in the AGB phase. So I used to work with Peter Wood on this when I first started my PhD. This was way back when. So you don't see that kind of structure in these post-AGB systems to have that sort of a long period, like the sequence D kind of period, I'm guessing is what you're talking about. Yeah, so we don't see that here. And also, if you look at the dust excesses and the shape of the SEDs, they're quite different for your AGB and for this one. So I'd say the physics of what drives your sequence D kind of long period is more mass loss pulsations, and we don't see that here. Also, I believe the AGB pulsations in general, they're kind of different to type 2 Cepheid pulsations. So again, just different. Yeah, but you're right, the 600-day period is very sequence D.
Have you seen or looked at, studied the Rotten-Egg Nebula? Do you think is sequence, which is like a post-AGB, early PNE, but actually it's still an AGB star in there, and they know what the companion is doing. Yeah. System.
Not personally, but I've read their works, and I think with something like the Rotten-Egg Nebula, the progenitor, they believe, comes from post-AGB, post-RGB. So there's always a link there. It's just...
Yeah, it's like an ongoing AGB stuff, but it might be the kind of thing that turns into your...
Yeah. With the rotten egg, it has a very, remind me again, it has quite a bipolar, it's got a,
And an A-type companion.
Yeah, if I can just, so there's there's an image, and we've got only one such image. Maybe I can show this. So this is one of the post-AGB systems. So this is a talk from Hans, and yeah, I was intrigued by this image as well. So it's a recent paper from Sahai where they study a IRIS-08, which is essentially the poster child that I've been showing you for all the interferometric imaging and sphere, and he's managed to get like this HST image of it, and it looks a bit like this. So you can kind of see that bipolar. So yeah, but again, the orbital period for this system is a little bit more larger, but yeah, likely that they have evolutionary links. Yeah, it's just it's ridiculously hard to get different groups of star people to work together. That's just my understanding, but I'm out on a mission, so maybe it'll all work out in the end. But yeah.
The disks, you mentioned that they're sort of on the massive end compared to traditional photoelectric.
Yeah, I don't know, maybe Dan or Christoph have a better insight. So we find the disk masses to be about 10 to the power minus 2 m-sun. Now, my quick sort of understanding is the protoplanetary disks are a bit more, a range of disk masses, so a bit more massive than ours.
We're around Saturn as well.
Okay, okay.
I was wondering if you have an idea about the density differences, if there are any more similar densities that would affect the information.
I'm not sure of that one. I'll have to look. I mean, yeah, I don't think we have particular constraints on density that I felt like I should compare, but that's a good thing. I can maybe have a look. Sorry?
You have an M dot one.
Yeah, we do. Yeah, so that shouldn't be so hard to get. Yeah. Mm-hmm.
What is your M dot there?
10 power minus 5 to 10 power minus 8 m-sun per year. So
10 to the minus 5 would be very high for us, but 10 to the minus 8
Okay.
would be typical.
okay. Yeah, so we get mass loss rates through different ways. We get mass loss rates from the modeling, of course, but we also get it from jets. So that's something I didn't show, but yeah, another time. But so our mass loss rates are quite well constrained, even though they're quite broad. But yeah, I mean, I would expect the densities are sort of similar, because if you look at the pressure scale height estimates, and we have only a few systems, they're sort of similar to PPDs. I don't know if I have maybe I do. I think Katya's paper that she just submitted today kind of gets around 90 AU for height of the disk. So I guess it depends on transition versus full. This one's like a full disk, so I don't know if that adds to the density. I'll have to think about that one, but I will. Yeah, thank you.